my name is Peter Irvine, and I'm a PhD student at Bristol University. And I got a World University Network Research Mobility Program scholarship or award in autumn 2010, where I went to Penn State University. And whilst I was over there, I worked with Professor Klaus Keller and Ryan Shriver for the most part. But as an added bonus, I also worked with Nancy Tuana and Toby Sadoba. So I'll just get on and explain what, first of all, geoengineering is, and then I'll go into what I did. So my PhD is on geoengineering, and this is perhaps best summed up by this quote I have here, which is, geoengineering is the deliberate modification of the Earth system to mitigate the effects of global warming. Now, that's quite an audacious proposal. So basically the idea is to engineer the Earth to undo the effects of the pollution we're adding. So the idea that I look at in my PhD is that if you reflect sunlight from the Earth, you're going to cool the planet, which is fairly simple, an idea, but has quite complex consequences, and of course would be quite hard to do. But I'm just going to talk about if you could do it, what would happen. So here we have two plots. On the left is the Earth's energy balance, a cartoon of it in its a normal state. We have sunlight coming in, some of which absorb, or most of which is absorbed, and then re-emitted as infrared radiation, thermal radiation. And this is trapped to some extent by greenhouse gases, natural greenhouse gases in the atmosphere. Now, we're adding CO2 to the atmosphere, which is trapping more of this outgoing radiation and acting to warm the planet. So if we could stop as much energy getting in the first place by reflecting sunlight before it reaches the Earth, we could control the Earth's temperature and cool it down. So what this type of geoengineering offers, in effect, is a thermostat to control the Earth's temperature. Now, it seems like potentially a good idea on the face of it, but it has a number of sort of complex consequences. And we were trying to explore some of those in our proposal. So the project was proposed and then developed with me and Klaus Keller. And we had sort of three parts to our proposal. First, we're going to develop a set of geoengineering scenarios, a set of ways to control this global thermostat. And this would require some modification of a model, the climate model we would use. Secondly, we would add some elements to the model that it didn't already have to represent sea level rise. So this is composed of the heating up of the ocean and thus its expansion, but also by adding mass to the ocean when you melt ice that's on the land. So we'd add those components to the model, and then we would look how the world's surface air temperature, or SAT, responds, as well as how its sea level responds, how the sea level would go up or down depending on how we control this thermostat. And the idea was then to look at these outputs and do some kind of economic analysis on it. Now, over the course of the project, we got the first two parts done, and we didn't have time to get onto the economic analysis, but we felt that there was enough interesting and novel information in this second part that we could publish a paper. And in the years since I completed this in December 2010, we've just had the paper published in Nature Climate Change just last month. So that's, in fact, just last week even. So that's just now completing, but thanks. So we may get around to doing the economic analysis at some point, but at this stage we've effectively wrapped up the project, but it could continue. So I'm going to show a little bit about what we found and exactly why it was interesting. So one of the basic problems, there's quite a few to geoengineering, but one of the basic problems is that the heat capacity of the ocean is much, much greater than the heat capacity of the atmosphere. So if you are changing this global thermostat, the surface air temperature will respond quite quickly to changes, whereas the sea level will respond much more slowly. That's because it takes a long time for the ocean to warm up, and it takes a long time to melt the ice on the land. So here we have the results, some of the results we got. So on this bottom plot on the left, we have the response of surface air temperature to these different scenarios. So the red uppermost scenario is the business as usual high CO2 scenario. We see a warming world. And this green one is if you have, as a scenario, of very strong mitigation, so very large cutbacks in emissions of CO2. And you can see that temperature will sort of more or less stabilize by the end of the 21st century. And then we had our two geoengineering scenarios. One in blue is a more moderate scenario, designed to be about equal to that mitigation scenario, so we stabilize temperatures. And a much stronger one, which has a very rapid cooling at first and settles at a much lower temperature. Now, we kind of make the argument that the cooler the better is not necessarily true. This rapid cooling could potentially be as dangerous as a rapid warming because it takes a long time for agriculture to adjust to changes and for ecosystems and plants to adjust. So potentially that rapid cooling is not a good thing, and this more moderate scenario is better. But when we look at sea level rise, we find that because of the way it responds, you see here with the business as usual case, we get quite a large increase in sea level, but for our mitigation scenario and our moderate geoengineering scenario, we still have significant increase in sea level. Whereas only the stronger geoengineering case do we halt the sea level rise. So we find this tension between these two goals. So if you want to really achieve sea level rise, you're going to overshoot on temperature, and vice versa. If you don't, you're not going to do enough if you just stabilize temperature to sea level rise. Another consequence of having this relatively low heat capacity of the atmosphere is that if you were to ever shut down geoengineering at some point in the future because of some unintended consequence, for example, if it affected ozone levels, and you decided to draw it back, you'd be faced with a very rapid warming because the Earth is trying to adjust from this cooler condition up to this warmer condition here. And so we chose a number of scenarios deciding on how quickly we turn our thermostat back to normal. And so we found very, very rapid rates of warming for a quick turn-off. It was up to 5 times faster than the business as usual rate, which is potentially very disastrous. So you're kind of left with this, you're caught between two things. Either you're faced with a rapid warming, or you have a long commitment to whatever it was that you thought was bad about geoengineering. So we find another tension in our results. And as I mentioned, we got this published last week. Our title was Tension Between Reducing Sea Level Rise and Global Warming Through Solar Radiation Management, which is another word for the geoengineering type we're looking at. So that was the main part of the proposal and what we were trying to do, and we achieved it. But we had a number of other things come out of it that were really quite good. And one of the surprising ones that I think was very good was an ethics collaboration. Now, Penn State had an existing collaboration that was beginning and ongoing between the ethics department and the geoscience department, between mainly Professor Nancy Tuana and Klaus Keller, but also their groups as a whole were becoming more meshed together. And this was really quite exciting because it was quite an interdisciplinary thing and allowed me to think about some aspects of my research, which is obviously very controversial from an ethics point of view. And over the course of my visit and since, we've been working on 2 papers that are on their way to being published. They're not quite there yet, but looking at how we could do an integrated ethical and scientific analysis of geoengineering, for one case, in a large group. And myself and Toby Sadoba are working on the technical and ethical challenges for compensation of geoengineering. So that was an unexpected, but I think perhaps the most significant outcome of the WN visit. One of the other outcomes is that some of the stuff I developed, some of the tools I developed on my exchange visit, I've taken back to Bristol, and they're now being used here. So myself, but mainly Elena Couthé and Lauren Gogar, are using the model I used, but applying it to the question of what would be the effects on coral reefs of this warmer, high CO2 world that's been cooled. Would it help coral reefs or would it harm them? And we're just starting to get the initial results, but it seems that crudely, higher temperatures and ocean acidification both harm corals. And in a world that has high CO2, you'll have both effects. But in a world with high CO2 plus geoengineering, you're going to reduce that sea surface temperature change. And so you're going to end up with a better situation for corals, which is an interesting result. And hopefully we should get something out of that over the next few months. So to sort of summarize, this World University Network visit made a lot of things possible that would not have otherwise happened. We got this Nature Climate Change paper that's been published. I've got involved in this ethics collaboration, which has been really interesting. I developed some research tools that hopefully I will use in the future and that others can use, and they're now being used in Bristol. And I think, I helped, I've linked up a bit with the people in Penn State, of course, but I think if there's now more connection between Bristol and particularly the geoscience department in Penn State. And I think in other ways it was a great experience for visiting a foreign country and seeing how they do things differently over there. It's been really great. So I'd like to thank you all for listening and thank the WN for making it possible.